Upward trends demand for new medicine enthuse chemists to develop synthetic tools to build more complex molecules. For instance, look at this monster. Palytoxin is one of the most toxic non-protein compounds and contains one of the longest carbon chain of naturally occurring molecules. It contains 64 stereocenters, so it can exist as over 10 to the power of 19 stereoisomers. Thus, for building such a complex structure, we should go further from classic synthetic methods and draw out new strategies with the aim of increasing efficiency. Whereas in the early days only simple molecules could be prepared, synthetic chemistry has arrived at the point that we can build everything we want. The question today is not only what can be built, but how do we do it? In this regard, the main challenge that involves chemists is efficiency, which can be defined as the increase of complexity per transformation. So moving forward with increasing complexity in molecular structures, synthetic chemists are always looking for new strategies. Imagine asking you to build this structure. In a normal procedure, you should design a stepwise formation of individual bonds with workup stage after each transformation. In contrast, modern synthesis enables us to form several bonds just in one process without the addition of any further reagent or catalyst, and without changing the reaction conditions. We have defined this type of transformation as a domino reaction. In analogy with domino games, in a domino process, the ladder transformations take place at the functionalities obtained in the former bond-forming reactions. Domino reactions are not a new invention. Nature as a chemist has been using this approach for billions of years. Lanosterol has been identified as a key component in maintaining island scalarity. In its biosynthesis pathway, 2,3-oxidosqualene is converted to lanosterol in a domino process in which lanosterol synthase enzyme catalyzes this transformation. As you see in this beautiful reaction, 4 carbon-carbon bonds form during cyclization process with high-level accuracy of installing stereocenters. Mapping out such an effective synthesis plan is on the wish list of every chemist. Now let's break down some synthesis routes based on domino reactions. In 2002, Overman group designed an interesting domino process based on pre-cyclization, which was followed by a pinnacle rearrangement to achieve cycloheptanone fused to a 2-substituted cyclopentane ring. The idea is using an appropriate activator like a base to produce a cationic Ch-like transition state. Poor electron density of this group and proximity to a donor group set the stage for the pre-cyclization. Next, appropriate orientation of carbocationic center and carbon-oxygen bond leads to pinnacle rearrangement, and our domino reached to the end. Designing starting materials and installing appropriate functional group on it is the key of running an effective domino process. In this case, by playing with the starting materials and put different functional group onto it, we can achieve broad range of diversity in target molecules, especially substitution in 2 position of cyclopentane ring. In one of the interesting variants, a mite group is installed in this position, and hydroxy group is protected by triethylsilyl. For reason of simplicity, triethylsilyl group is shown by a purple sphere. First off, ketiminium ion intermediate is produced in reaction with triphylic anhydride, and make use of DTBMP as a hindrance base. In this step, double bond attacks of this carbon atom and produces carbonium ion through a Ch-like conformer. After that, pinnacle rearrangements, a 4-cycloheptanone fused to the cyclopentane ring. This intermediate is protonated under reaction condition to give iminium salt, which is hydrolyzed upon treatment with aqueous base. Finally, domino ends up with introducing carbonyl group in 2 position of cyclopentane ring. The outstanding feature of this domino is its high diastereoselectivity. As you see, hydrogen and methyl are cis together in final product. Maybe you think that transform is more stable, so what is the origin of such a high diastereoselectivity? To rationalize, let's take a look at the cyclization step. As you see, this intermediate adopts a Ch-like conformation, in which there are 2 options for orienting of methyl group. When it is in pseudo-equatorial position, serious steric hindrance arises between triethylsilyl and methyl group, so it prefers to adopt pseudoaxial position to minimize steric hindrance. Due to this orientation, methyl and hydrogen are in the same plane, which leads to cis product. This domino began with the simple starting material. By adding triphylic anhydride and a base, we can produce a high valuable structure with high diastereoselectivity. Imagine how many steps are needed to produce this target in a normal procedure. Moreover, we can introduce different functionalities in the final product by installing different functional groups in the starting material. And this is the power of the domino process. Another interesting domino reaction reported by Carrenƒo group in the same year, based on using chiral sulfoxide to produce stereoselective heterocyclic H compounds. In the first step of designing a starting material, LEA abstracts a proton from methyl group of sulfoxide. Then it attacks to the benzoquinone monoamine compound. Second step is unmasking of carbonyl group by oxalic acid. Finally, amine group is deprotected by trifluoroacetic acid. The starting material consists of two chiral atoms. We can control a stereochemistry of S atom by using an antiomeric pure sulfonyl compound. But the imine bond is equally attacked from below and above the plane of the double bond, resulting in two diasteromers which are separated by a chiral column chromatography. Another feature of a starting material is that we can use free substituted benzoquinone monoamine compound, which plays an important role in diastereoselectivity of the reaction. Reaction of benzoquinone monoamine with 2-tetramethylsiloxyfuran starts the domino. Firstly, tetrabutyl ammonium fluoride cleavages the silicon-oxygen bond and prompts a Michael addition. The newly formed butanolide framework is then attacked by the amino moiety in a second Michael manner to give an enolate, which in a third Michael addition affords the KH compound. Now let's go over a stereochemistry of the reaction. In the first Michael addition, there is two sites for attacking furan, so the product exists as two diasteromers. But in the substituted benzoquinone structure, Michael addition exclusively takes place in the less inert site. Due to this bias in the molecule, only one diasteromer is produced. Another interesting feature of this reaction is high pi-facially diastereoselectivity in both substituted and unsubstituted benzoquinone structure. It means that Michael addition takes place from the face of the amine group, because the sulfoxide moiety blocks this face of the molecule. Pagodane is such a complex structure with high point group symmetry and has close relationship with dodecahedron, an entirely pentagonal structure. This polycyclic framework comes with noteworthy structural peculiarities. The central cyclopentane ring forms part of several propylene substructures. In addition, each of the quaternary carbon atoms form the center of a 5-5-5-5 fenestrine unit, and every side of the four-membered ring is spanned by a free carbon chain, thus constituting a tetraaniline unit. Carrenƒo synthesized this complex structure for the first time in 1987 over 17 steps. He starts with izodrine to produce this starting material. Due to structural rigidity, two six-membered rings are fixed to the cyclobutane. This rigidity sets the stage for precyclic type reactions. Domino begins with adding of maleic anhydride, which reacts with one of the diene moiety of the six-membered ring, with endoselectivity as a result of intermolecular Diels-Alder reaction, and ends up with connection of two rings by the second Diels-Alder reaction in an intramolecular fashion. Carrenƒo used this structure to produce Pagodane.